Far beyond our sun, a colossal red hypergiant called RW Cephei is living its final days. It burns slowly, fading into the quiet of space, a dying titan among the stars. Tonight we'll uncover the story of one of the largest stars ever known. If you enjoy this cosmic journey, please like, subscribe and share, and tell us in the comments, what would you ask a dying star if it could answer? Thank you for watching. Now, let's begin. The Milky Way stretches as a broad barred spiral, and within its patterned arms, the Perseus arm winds as one of the major star-forming lanes, a quiet river of gas and dust on galactic scales, where bright clusters, dark filaments and glowing nebulae mark places of recent and ongoing birth. In this arm, far from the brilliant congestion of the central bar near Sagittarius, a star lies the region of Cepheus high in the northern sky, where the field thins just enough to reveal knots of activity against a mottled backdrop of starlight. In this setting, the gas of the diffuse interstellar medium gathers under gravity into long strands, and those strands splinter into clumps as pressure waves pass, leaving arcs, ridges and cavities that testify to past episodes of star formation. Shocks from earlier generations of massive stars open bubbles and compress their rims, so that the arm shows not a simple spiral lane, but a stitched tapestry of shells and fronts that move energy outward and seed fresh pockets where stars can grow. The Perseus arm turns at a gentle pitch angle around the galactic center, and as it curves it carries along reservoirs of hydrogen in different phases, from cold molecular cores to warm atomic clouds that drift through a radiation field shaped by the brightest young stars. Dust grains mix through it as small solid particles of carbonaceous and silicate material, and these grains provide surfaces where molecules assemble, and where starlight is absorbed and re-emitted as a faint infrared glow, so that even places that appear dark in visible light shine softly at longer wavelengths. Spiral density waves, which are regions where material slows and crowds for a time, help explain why the arm hosts repeated star formation, because where gas lingers, it becomes more likely to cool, condense and collapse. Over millions of years, the pattern of the arm advances like a traffic wave, while individual stars, gas clouds and clusters move in and out, leaving an imprint of arcs and spurs that point away from the main lane and carry young groups into the surrounding disk. The solar system sits in the Orion Cygnus spur between two major arms, and the Perseus arm lies beyond as seen from Earth, so lines of sight pass through long stretches of intervening dust that redden and dim starlight. Yet in windows where extinction falls, observers can trace H2 regions, reflection, nebulae and star clusters that map the arm's skeleton, outlining how gravity and feedback balance to regulate the pace of starbirth in this part of the galaxy. Cepheus stands along this outer reach bounded on the sky by Cassiopeia, Draco and Cygnus, and it hosts a patchwork of emission clouds where young massive stars ionize hydrogen, making it glow with a soft red light, while nearby dark clouds remain cold and opaque. The contrast between luminous cavities and veiled lanes shows how unevenly energy and matter are distributed, and how local history matters as much as global structure, to set the present conditions in which a luminous, cool hypergiant now resides. On the larger scales, differential rotation shears the arm, while turbulence stirred by supernova remnants expanding H2 regions and stellar winds works down to smaller scales, breaking smooth flows into eddies and shocks. In that cascade, molecular clouds assemble into complexes tens to hundreds of light years wide, and within them denser clumps form that will eventually host clusters and associations whose most massive members live brief, bright lives, and then feed back momentum heat and heavy elements to the arm that made them, The abundance pattern in the outer disk remains slightly lower in heavy elements than the inner regions closer to the bar, a gradual gradient that traces the chemical enrichment history of the galaxy. Yet even here the raw materials for dust and molecules are plentiful, and observations across radio-infrared and optical bands show carbon monoxide polycyclic aromatic features and ionized lines that together sketch a living ecology of gas phases interacting under radiation and gravity. The Perseus arm's position relative to the galactic bar influences the streaming motions of gas, so velocities measured along sightlines do not match a simple circular model. Instead, they show gentle offsets that reveal the presence of the density wave and of the local perturbations, and those offsets, when mapped, help determine distances to clouds and clusters with better confidence than brightness alone would allow, which matters greatly in regions where extinction hides much of the light. In this arm, clusters such as those found in Cepheus trace recent star formation over the past few tens of millions of years, and their brightest members carve cavities whose rims glow as thin curving sheets. Near those rims where pressure rises, further collapse proceeds, setting off sequential star formation that travels across a complex like a slow front and leaving age gradients that record the motion of energy through the medium. The magnetic field of the galactic disk threads the arm as faintly ordered lines that guide charged particles and shape how gas compresses. So filaments often align along preferred directions, and polarization measurements of starlight and dust emission reveal that alignment as a subtle signature atop the intensity maps. This field, though weak compared with thermal and turbulent pressures in many places, still influences the birthplaces of stars through its effect on support and flow. Seen from above, the Perseus arm looks like a sweeping lane braided with spurs, but from within the disk the perspective compresses structures along long sightlines, making distinct regions overlap. Unravelling that projection demands multi-wavelength views and careful modelling, and across those views the arm consistently appears as a location where the balance of cool, dense gas and young luminous stars tips toward active formation without reaching the extreme intensity of the inner ring near the ends of the bar. Energy from hot stars drives photo-ionization fronts into adjacent clouds, and the resulting pressure differences launch, flows back into the arm. Dust grains pushed by radiation and carried by gas drift into diffuse halos around the bright clusters, and those halos scatter blue light and glow in the infrared, leaving a two-color signature that marks how young stars reshape their cradles even before the most massive among them end their lives. Over time, the injection of momentum from winds and explosions puffs the arm's mid-plane, creating a layered vertical structure, where warm and hot gas vent into the halo through chimneys, while cold, dense material sinks toward the plane. This circulation moderates the rate at which new cold clouds can assemble, and the resulting rhythm of formation and dispersal keeps the arm from locking into either a quiet phase or an all-out burst. The arm's kinematics also carry star groups together for a time as loose associations that drift apart over tens of millions of years. During that window-shared motion allows astronomers to tie related objects into coherent histories, and in Cepheus, such links outline families of clusters and massive stars that trace the recent record of the region as one episode follows another, each leaving shells, dust arcs, and enriched gas in its wake. The light that crosses this arm to reach Earth carries the imprint of dust and gas along the way, so spectral lines from interstellar calcium, sodium, and molecules appear superposed on stellar spectra, and diffuse interstellar bands mark complex chemistry not yet fully identified. These features read together tell the story of distances, reddening, and intervening structure that must be accounted for to place any luminous star correctly within the arm's framework. The Perseus arm thus provides the immediate galactic context in which a cool, extremely luminous and very extended star can exist, because it supplies the raw material for the formation of very massive stars and the feedback environment that shapes their surroundings. Its lanes of molecular gas, its networks of bubbles and shells, and its moderate but persistent pace of star birth enable the presence of regions where rare giants live for a brief time and imprint their signature across the medium. In Cepheus, the interplay of arm-scale flows, local feedback, and line-of-sight extinction sets the stage for the view so that any given night sky image of the area shows a mosaic of glowing hydrogen, scattered starlight, dark dust, and field stars at a range of distances across the disk. Against this backdrop, the Perseus arm structure anchors position and defines the conditions of light and shadow, heat and coolness, motion and rest that frame the scene before any attention turns from the arm to more specific neighbourhoods within it. The ionized complex, catalogued as Sharpless 2132, spreads across Cepheus as a soft irregular glow, a mesh of hydrogen lit by hot stars and threaded with dark lanes where dust slows the advance of light. Deep images show arcs and rims, while radio and infrared maps reveal shells and cavities that record long pressure waves. Along bright edges, radiation pushes into denser clouds and sculpts curved fronts. Gas becomes ionized near the stars, then cools and recombines farther from the sources, leaving a graded skin that shines in recombination light and in the warmth of dust. The fronts do not move smoothly, because density varies from place to place. They scallop, break into beads, and cast shadowed fingers into the interior where cooler material persists. The complex lies within a larger association of clouds and young groups that share similar velocities along the line of sight, though precise relationships remain under study because the field holds patchy extinction and overlapping structures. Compact clusters sit near several luminous arcs, and looser families of bright blue stars drift farther out their winds, and radiation shaping the cavities that now shine. Ages differ by only a few million years from group to group, suggesting repeated episodes across the same cloud complex rather than a single burst. Yet the present scene looks continuous, with one generation's cavities pressing on the next reservoir and setting up the rims that glow today. Beyond the brightest rims lies a low-surface brightness sea, where dust temperatures fall and gas becomes diffuse. Small knots linger where denser clumps resist erosion, and between them faint filaments extend for many light years, shaped in part by a weakly ordered magnetic field that aligns grains and nudges flows along preferred directions. Though the field is gentle compared with thermal and turbulent pressures, it adds structure to the way fronts advance and clouds fragment, as seen in the tendency of filaments to track similar angles across wide patches of the nebula. Signs of ongoing birth are common. Infrared catalogues list young stellar objects with warm dust, some driving narrow jets, that collide with their surroundings and light compact shocks. Along the swept-up edges of bubbles, ridges become dense enough to collapse, and small clusters arise in curved chains that trace the paths of advancing fronts. Where a front meets a denser knot at an angle, a pillar grows, pointing back toward the ionizing stars. These features erode over time, shedding clumps that feed the interior while preserving the overall direction set by the radiation field. Multi-wavelength maps knit the scene. Radio continuum traces thermal electrons and confirms the photoionized nature of the arcs, while radio recombination lines add velocities that show gentle expansion from interior cavities. Molecular lines reveal where cold gas piles up ahead of the fronts, and where interior gas has broken through thinner walls. Mid-infrared spectra pick up broad features from complex aromatic molecules, brightest along the rims and cavity walls, while far-infrared emission and sub-millimeter maps outline the cold reservoirs that wait in shadowed lanes. In visible light, the complex can look fragmented because dark lanes slice emission into discrete pieces and foreground clouds cast irregular shadows. Correcting for extinction by using star colors and emission ratios reassembles broad arcs into coherent structures. Several shells overlap their edges brightest where viewed tangentially. Some rims show openings where energy has found easier paths, and there the gas streams outward, thinning the shell and feeding a larger network of diffuse glow that wraps the brighter cores. The outlines of these cavities rarely form perfect circles. Instead, they show offsets and box-like segments, in places a sign that the density field into which they expand is far from uniform. On larger scales, the complex sits within the flow of the Perseus arm. Streaming motions slightly shift measured velocities away from pure circular rotation, so spectra must be modelled with care to estimate distance. Together with patchy extinction, this leaves room for more than one placement in the literature. Even so, the grouping of clusters and nebulae on the sky and the similar velocities of gas and stars argue for a connected association that spans many tens of light years and has been active for many millions of years. The surrounding field adds further patches of faint emission and dark clouds with similar motions, marking a wider ecosystem of star formation. Here the balance between bright ionized cavities and thick infrared luminous dust lanes creates sharp contrasts useful for tracing the handoff between ionized gas warm molecular skins and cold cores. Because different tracers emphasize different layers, the region serves as a clean laboratory, where the flow of energy can be followed from the ionizing sources out through the fronts and into the cooled compressed gas that may seed the next sites of collapse. Set against this layered scene, a very luminous cool star appears in projection near prominent structures, and is often discussed alongside nearby clusters and the broader association. Whether it is bound to a particular group loosely associated or offset along the same sightline depends on refined distances and motions. With present uncertainties, more than one arrangement remains possible, so placement is handled with care. For environmental framing, it is enough that the line of sight crosses an active complex of ionized gas-warm dust and cold molecular material shaped by massive stars and their feedback, providing a natural context of light, shadow, and motion. Observers separate these layers by tuning to distinct spectral lines and bands. Hydrogen recombination light outlines the broad sheets, doubly ionized oxygen singles out the hottest interior gas, and singly ionized sulfur marks the denser transition zones where the front slows. In the infrared, emission from warm dust and from complex aromatic molecules wraps the arcs in a soft glow, while far infrared and sub-millimeter maps reveal the cold reservoirs that still await collapse. Kinematic maps built from these tracers show that the nebula's brightest arcs move only slowly at speeds of a few kilometers per second, consistent with fronts expanding into clumpy material and venting through the thinner spots, while cold gas behind the fronts gathers into curved ridges that mark the next places where gravity will take hold. In this wider neighborhood, several named clusters and associations, including candidates in the Berkeley Catalogue and members of the Cepheus Association, appear in similar directions on the sky. Some may be physically connected, others only aligned by chance through the disk, and present data allow careful discussion without firm assignment. This neighborhood frames the view with its mix of bright cavities and shadowed lanes, and sets the conditions of light motion and dust along the sightline. The question of how a solitary, very luminous cool star fits into the surrounding stellar families in Cepheus turns on membership and membership depends on distance motion and age that are each difficult to pin down along this crowded arm. The candidate links most often discussed include the compact cluster catalogued as Berkeley 94 and the broader loose grouping called Cepheus OB1, both lying in similar directions and both embedded in a web of gas and dust that further confuses the view. Observers approach the problem by assembling several lines of evidence photometric sequences that reveal cluster ages through color magnitude diagrams, spectroscopic classifications that turn brightness and temperature into distance estimates, when extinction is understood, radial velocities that trace motion along the line of sight, and proper motions that track motion across the sky. None of these alone settles the matter because each carries systematic errors in this field, but together they frame ranges where association remains plausible. For the compact cluster, the stellar sequence of bright blue members yields an age of only a few million to some tens of millions of years, consistent with ongoing activity in the nearby ionized complex. Its distance estimates cluster around values that place it within the Perseus arm, while reddening maps show substantial and uneven dust along the sightline, meaning that stars even within the same apparent group can suffer different levels of dimming and color shift. The luminous cool star in question being enshrouded by its own dust and showing irregular circumstellar extinction presents additional complications. Standard color-based methods assume clear photospheres, while here circumstellar grains absorb and scatter light in ways that alter apparent temperature and brightness. Furthermore, the star's size and surface structure vary over time, changing its flux and angular diameter, so distance solutions based on fits to spectral energy distributions inherit extra uncertainty. Precision astrometry from modern surveys improves the situation in many fields, yet for very bright, highly reddened and large angular diameter stars with complex photometric behavior, parallax measurements can be biased, and correlations among solution parameters can inflate errors. Careful treatments that fold in priors about location in the galaxy and compare independent methods therefore remain necessary, and recent analyses often present distance ranges rather than single values. If the star sits at approximately the same distance as Berkeley 94, then an explanation consistent with shared formation within the same larger cloud complex becomes attractive, with a compact cluster representing a dense knot in a broader star-forming episode that also generated more dispersed massive stars. If the star instead lies somewhat ahead, or behind still within the same arm segment, then it may be related through the wider Cepheus-OB association, or it may only project across that field its true birthplace, potentially another older knot whose gas has since dispersed. The wider association catalogued through common proper motion and shared early type spectra spans large angles on the sky, and includes multiple subgroups with slightly different ages, which is typical for regions where star formation proceeds in waves driven by feedback and cloud flow. Within such a structure, a luminous cool hypergiant can be either a surviving massive member that has evolved off the main sequence, or a traveller that drifted from its birthplace, and without precise three-dimensional velocities and distances, the distinction remains open. Radial velocities measured from the star's spectra are themselves influenced by atmospheric motions, winds, and asymmetric line profiles, complicating comparisons to cluster means. Absorption features from intervening interstellar gas add further lines that must be separated from stellar lines, and small differences in adopted templates can shift reported velocities by a few kilometers per second, which matters when clusters have low internal dispersions. Proper motions can help by showing whether the star moves like the cluster members across the sky, yet at these distances the expected angular motions are small, and measurement systematics coupled with the star's brightness and variability place cautious limits on the precision, so overlap within uncertainties cannot be taken as proof of membership, while offset within uncertainties cannot be taken as proof against it. Age offers a complementary angle. The cluster's young sequence points to recent formation, while the cool hypergiant's current state implies an evolved massive star that has moved beyond its hot youth. Those states can be consistent if the star began life with very high mass and evolved quickly, but they can also be consistent if the star does not belong, and instead formed in an earlier burst within the same wider complex, leaving it older than the compact cluster while still residing in the same direction. Extinction estimates across the field show significant variation over small angular scales, with dust lanes and clumpy clouds adding differential reddening that bends color sequences and broadens them. Work that corrects these effects reconstructs tighter cluster sequences and refines distance and age. Yet, for the hypergiant, the internal dust shell and episodic ejections add a local time-dependent layer that must be modelled separately, making direct comparison to cluster values an exercise in careful partitioning of what part of the dimming comes from the interstellar path and what part comes from the circumstellar environment. In this context, studies often adopt a pragmatic approach. They present distances for the star based on multiple methods. Note the overlap or tension with distances to Berkeley 94 and to representative subgroups of Cepheus OB1, and then discuss the likelihood of physical connection in terms of consistency rather than assertion. In many cases, the star falls within the distance ranges of the nearby cluster and association when broad uncertainties are included, but the error bars do not allow a definitive tie. Spatially, the star lies close on the sky to bright arcs of ionized gas, and to listed members of the compact cluster, and deep images show a field crowded with early type stars and patches of emission that make a physical link plausible. However, chance alignment with arm structures can mimic proximity, and the long lines of sight through the disk mean that projection effects are common, even in regions that look coherent in visible light. The dynamic history of the wider association also bears on this question. Loose groups disperse over tens of millions of years, carrying their members into broader orbits that blur the edges of the original formation site, so a present-day map of members should be read as a snapshot of a moving flow, rather than a fixed cluster, and a luminous evolved star could reasonably be either a trailing survivor or a neighbor born in a sister knot. On balance, the cautious statement remains that the hypergiant appears in a direction rich with young and recently formed populations whose distances and motions overlap with the ranges obtained for the star itself, that a physical link is possible and even attractive, and that more precise parallax improved treatment of its complex photometry and simultaneous modelling of its spectral line velocities and wind signatures will be needed to move the case beyond plausibility. Until then, the field around the star serves as a practical frame. Compact clusters, loose associations, bright arcs and dark lanes all share the sightline, and the star's light must cross them, picking up their imprint while its own environment also shapes what is seen. That double layering of interstellar and circumstellar effects sets the tone for any analysis and explains why membership remains a careful incremental question rather than a settled fact. Within the narrative of the region, this section holds the camera steady on the networks of related stars and the paths they trace across the arm, allowing the star's possible ties to be weighed against the structure of the neighborhood and leaving the next step to narrow from these wide associations to the material that immediately surrounds the luminous source. Around the luminous, cool hypergiant, a faint architecture of dust gathers and glows, forming shells, arcs and diffuse veils that are easiest to trace at mid and far infrared wavelengths, where warmed grains re-radiate the starlight they absorb. In visible light, the material often appears only as a soft dimming or a subtle reddening. But in the infrared, the circumstellar region becomes a low-contrast halo with knots and asymmetries that speak of an outflow history written over many episodes. The dust itself consists of tiny solid particles, mixtures of silicate and carbonaceous grains, with sizes typically smaller than a micron, and these grains both absorb and scatter light, shaping the star's apparent brightness and colour in ways that change with wavelength. Closer to the star, where temperatures rise, grains can only survive if they can radiate the heat efficiently, so the innermost boundary of the dust zone stands at a radius set by the balance between heating and cooling. While farther out, cooler layers add a second and third band of emission that, together with the stellar light, build a spectral energy distribution with distinct humps. Imaging at mid-infrared wavelengths often reveals that the halo is not a perfect circle, but shows brighter sectors, arcs or box-like contours that point to directional outflows, or to the influence of large-scale motions in the extended atmosphere. The halo brightens where thicker columns of dust align along the line of sight, and fades where cavities thin the material, so the observed structure is a projection through a three-dimensional envelope whose depth cannot be seen directly, but can be inferred by modelling. In many hypergiants, the dust is carried outward by a slow, dense wind that leaves a near-steady background signal, while superposed on that background are denser clumps traced by warm knots. In this case, the map suggests a similar mix with a broadly distributed halo and local enhancements that stand out as patches a little warmer and brighter than their surroundings, consistent with recent condensations or with denser parcels launched from different parts of the surface. The geometry shows hints of preferred directions, a sign that surface motions and magnetic fields may channel the flow, or that the star's motion through its local medium imparts a slight drift that offsets the brightest dust downstream. Even a small space velocity through gas can produce a mild bow-like asymmetry that, when combined with episodic mass loss, leaves a layered wake on one side and a thinner veil on the other. Spectral energy distribution fits combine photometry from visible to far infrared bands and, when available, sub-millimeter points. These fits require a stellar photosphere diluted by distance and reddened by interstellar dust, plus one or more circumstellar components at temperatures that step down from a few hundred degrees Celsius near the inner boundary to tens of degrees Celsius in the far halo. The relative strength of these components changes as the amount of dust and its temperature change, so multi-epoch photometry can reveal how the inner zone brightens and cools as fresh grains nucleate and drift outward, while the outer zones evolve only slowly because their large radii average over many years. When the dust lies in compact shells rather than in a smooth distribution, the infrared light can vary in a way that lags behind optical changes, because the grains respond to the star's changing radiation field and to the travel time of material through the condensation zone. Such lags help locate the inner edge in physical units when combined with estimates of outflow speeds measured from spectral lines in the gas, tying the geometry to a timeline of ejection and drift. Polarization measurements add another dimension, since aligned or asymmetric grains scatter starlight in a way that imprints a preferred angle on the light. Small but measurable polarization across visible and near-infrared bands indicates that scattering by circumstellar dust contributes to the observed flux, and changes in degree or angle over time imply that the distribution of dust near the line of sight evolves, whether by fresh ejection, drift, or partial clearing. High angular resolution at mid-infrared wavelengths, achieved with large telescopes and careful image reconstruction, resolves the inner few thousand astronomical units around the star into bright clumps and arcs, while complementary interferometry at shorter wavelengths constrains the scale where dust first survives. Together, these views show that the circumstellar environment is not static or spherical, but patchy, with a brightness distribution that shifts over several years, pointing to a flow that is continually fed by the extended atmosphere and moulded by local dynamics as it leaves the star. The chemical makeup of the grains can be read in broad spectral features. Silicate emission produces wide bands around wavelengths, where the mineral lattice vibrates while carbon-rich material and complex aromatic molecules add distinct plateaus at mid-infrared wavelengths. Detections of these features vary with viewing angle and with the relative dominance of emission and absorption, but where they are seen they confirm that the dust includes silicate material, typical of cool oxygen, rich outflows from massive stars mixed with other species that either condense later or form in different parts of the flow. The outer halo, which glows at far infrared wavelengths, records older mass loss, because material there takes many years to cross even a small fraction of the distance it covers. Maps at these wavelengths often smooth over small-scale structure, but they reveal the overall size of the dust environment, which in very luminous stars can extend for a fraction of a light year, and sometimes merges into a fainter background of interstellar dust that has been stirred by the star's radiation and wind. Separating circumstellar dust from the larger interstellar field requires careful subtraction of background emission and a good understanding of the local cirrus structure, since the Perseus arm hosts extensive diffuse dust that emits in the same bands. Techniques include measuring the brightness profile around the star and comparing it with nearby fields, modelling the point spread function to remove the stellar core, and examining colour ratios that differ between warm circumstellar grains and cooler interstellar filaments. When this separation is done, the remaining halo brightness sets constraints on the mass of dust present, and by assuming a gas-to-dust ratio appropriate for massive cool winds on the mass carried outward. Those estimates carry uncertainties because grain composition, size, distribution and clumping all change the inferred mass for a given brightness. Yet even with conservative assumptions, the values point to substantial material surrounding the star. Some arcs break into beads or knots that trace instabilities as the dense shell expands into a lower pressure medium, and these beads can line up along segments that approximate circles or ellipses, suggesting that certain ejection events were coherent over a range of surface longitudes. Such patterns imply that the launch region on the star was extended rather than point-like, consistent with the presence of large convective cells that span a significant fraction of the surface of a hypergiant and feed outward flows over wide angles. In the innermost region, just beyond the radius where dust can survive, gas remains the primary carrier of the outflow, and the transition from gas only to gas plus dust shifts the opacity and the way radiation couples to the flow. Once grains form, they absorb starlight and transfer momentum to the gas through collisions, boosting acceleration and altering density profiles. So the appearance of the dust shell marks not only a change in emission, but also a change in the dynamics of the wind. Over time, the layered shells that result from varying outflow rates blur into one another as material drifts outward, cools and merges with older ejecta, leaving a stratified but continuous envelope. The outermost layers gradually approach the conditions of the ambient medium in the star-forming region, and at those distances the difference between circumstellar and interstellar dust becomes one of degree rather than kind. Inside the envelope, however, the signatures of recent activity stand out, and by mapping their positions and temperatures, it is possible to reconstruct a partial history of the flow over recent decades, connecting inner warm arcs to middle cool shells and to far outer diffuse halos that keep the imprint of events long past. In this section, the view remains fixed on those dusty layers, their temperatures, shapes, and slow motions, because they establish the immediate setting through which the stellar light must pass before it reaches the surrounding medium, and they provide the record against which any shorter-term changes closer to the star can later be understood. The record of how material leaves a very luminous, cool hypergiant unfolds in layers written into gas and dust, and that record can be read with methods that recover both present outflow and older episodes. Mass loss defined as the rate at which the star sheds matter into space, sets the density of the wind and the shape of the surrounding envelope over time, so estimates of that rate become the backbone of any timeline. Today, diagnostics that respond to ionized gas, neutral gas and dust each provide a piece of the picture. Thermal radio emission from free electrons, called free emission, rises gently with wavelength and traces ionized zones in the wind. Its brightness links to the rate at which particles stream outward, and to their velocity, since a faster wind spreads material more thinly, while a slower wind piles it up. Visible and near-infrared spectra record absorption and emission lines formed in the outflowing layers above the photosphere. When a line shows an emission core with a blue shifted absorption notch, a profile called a P-Cygni shape, it signals gas moving toward the observer that absorbs the stellar light, and the blue edge of that notch gives a measure of the wind's terminal speed, the speed the flow reaches far from the star. At longer wavelengths, dust warmed by starlight glows and adds a second route to the rate for a given grain makeup and size distribution, the infrared luminosity of the shell scales, with the mass carried outward, though clumping and temperature gradients complicate the conversion. By bringing these views together present day, mass loss emerges as a slow, dense flow, typical of cool hypergiants with speeds of only a few tens of kilometers per second, and rates high enough to build substantial shells over decades. Because the wind carries both gas and dust, the ratio of gas to dust matters, and a standard assumption places most of the mass in gas with dust, only a small fraction by weight yet dominant in setting opacity. When the dust forms, radiation pressure acting on grains transfers momentum to the gas through collisions, and that coupling helps drive the outflow. Observations that sample different distances from the star and thus different look-back times, because the wind takes years to cross the envelope, show that the density does not always follow the smooth inverse square law expected for a constant rate. Instead, there are departures that imply changes in the flow, with denser zones marking intervals of elevated shedding and thinner zones marking quieter phases. Archival images in the infrared reveal that the far outer halo holds enough mass to require stronger activity in the past than the steady rate that best fits the inner warmer dust. When modelled with simple shells, the outer brightness can be matched by one or more old episodes in which the rate rose above the present value for a span of years. These episodes likely began near the extended atmosphere, where large convective cells and shocks modulate density and temperature. If conditions cross thresholds that favour grain nucleation, dust forms more efficiently, and the coupling between radiation and gas strengthens, allowing a brief surge in mass flux that then travels outward as a dense wave. Evidence for such surges comes not only from brightness, but also from the temperature structure of the dust. A dense inner shell restricts stellar light and shades material beyond making the outer dust cooler than it would be in a steady, optically thin flow. Mapping colour temperatures across the halo can therefore point to older ejections now sitting at large radii. The timeline of these features is set by the wind speed. For speeds of a few tens of kilometers per second, a shell needs decades to move from the condensation radius to distances where it blends with the older halo, so a chain of shells can represent a century-scale sequence of events. Historical spectra add hints of change. In some epochs, lines that form in the outflow strengthen or weaken, and their terminal velocities shift by a few kilometers per second. Those movements, though modest, alter the balance between density and speed for a given mass flux, and thus modify how the envelope builds. Photographic plates and early photoelectric measurements of brightness, once corrected for calibration differences and for interstellar extinction, show that the star's light fluctuates on timescales of months to years. While changes in the star's surface layers contribute part of the observed variation, can arise from the growth or thinning of dust along the line of sight, which itself reflects the near-term mass loss climate. Together, these strands support a picture in which the present rate, though high, sits below peaks that occurred within the past century, with at least one extended interval of stronger shedding needed to account for the mass inferred in the cool outer halo. The current reality appears as a layered outflow. A quasi-steady wind sets a baseline episodic enhancements, builds shells and arcs over several years, and smaller irregular clumps ride upon these patterns, clumping the tendency for matter to gather into denser pockets rather than remaining smooth, affects all rate estimates because emission processes scale non-linearly with density. If the gas is clumped, a given brightness implies less mass overall than in a smooth wind, so rates derived without allowing for clumping can be biased high. To compensate, analysts adopt a clumping factor that quantifies the density contrast between clumps and the mean. Even with conservative factors, the total amounts involved remain large enough to change the star's mass by a meaningful fraction over the short lifetimes of massive cool phases. The spatial patterns seen in mid-infrared images where arcs break into beads and bright knots line parts of a circle signal that instabilities in expanding shells also shape the record. As a compressed layer moves into lower pressure surroundings, perturbations grow and the shell corrugates, concentrating dust and gas into spots that glow more brightly. These instabilities do not change the total mass lost, but they change how observers reconstruct it, because brightness then depends on geometry as well as on content. Radial variations in composition matter too. If the inner shells show silicate features while outer shells show a different mix, the change hints that conditions at the condensation radius have shifted with time. A cooler or denser atmosphere favours certain grain species and sizes, and those choices set both opacity and temperature, which in turn influence how the next layers behave. Such feedbacks create a chain in which a phase of stronger mass loss modifies the radiation field that reaches greater distances, and the modified field sets the thermal history of older ejecta. A separate line of constraint comes from the scatter and polarization of starlight. When the inner envelope becomes optically thick to scattering, the fraction of light that reaches the observer directly from the photosphere drops, and the fraction that comes via scattering off nearby dust rises, increasing polarization and softening spectral signatures from the surface. Observers have reported changes in polarization degree and angle over intervals of years consistent with evolving dust near the line of sight, and compatible with a cycle in which fresh grains condense, drift outward and thin with distance. The overall budget implied by these indicators places the star among the most prodigious mass losers in the cool, very luminous class, with today's flow sufficient to build a substantial shell within a human lifetime, and with past stretches of enhanced shedding required to explain the extent and brightness of the far halo. Uncertainties remain driven by distance ranges, by clumping factors, and by assumptions about grain properties. So quoted rates are best presented as intervals rather than single numbers. Yet under any reasonable set of choices, the conclusion holds that the envelope we see is the product of sustained mass loss, punctuated by stronger events. A deep decline in visible light draws attention to the circumstellar environment, when the hypergiant enters a phase now called the Great Dimming, a period during which the star's apparent brightness falls by more than a magnitude in standard bands and then slowly recovers. The change is not sudden in a single night, but moves over weeks to months with the curve of brightness, forming a broad descent, a low plateau and a gradual rise that continues beyond the first season. The pattern coincides with shifts in colour that point toward dust condensation along the line of sight, because reddening increases as the light dims, and the ratio of change in different bands matches the behaviour expected. When an additional veil of warm grains forms and scatters and absorbs starlight, polarization grows during the descent as a larger fraction of the observed light arrives, after scattering off near stardust rather than directly from the photosphere. At the minimum, it reaches a peak and then relaxes during the recovery, a sequence consistent with fresh dust, forming close in and then drifting outward while thinning along the sightline. In parallel, mid-infrared measurements brighten slightly and show a warmer inner dust component indicating that new grains near the condensation radius absorb more energy and re-radiate it at longer wavelengths. The effect is modest but measurable, and it strengthens the case for a dust event rather than a dramatic cooling of the photosphere. Spectral lines formed in the outer atmosphere and wind also change. Baemer and metal lines develop profile asymmetries with blue shifted self-absorption, deepening at certain times, and low excitation lines associated with cooler gas strengthen. These signatures point to enhanced outflow and to a cooling more extended layer above the photosphere where condensable material accumulates. The terminal speed measured from the blue edges of wind-sensitive lines shifts by a few kilometers per second during the event, and this change modifies density and the flow. A slower wind yields denser inner zones for a given mass flux, which favors grain growth while a slight increase in flux adds more raw material. Multicolor photometric monitoring across many observatories knits a coherent light curve that captures both the deep minimum and secondary features such as small pauses in the descent and minor brightenings within the low phase. Those fine structures are compatible with clump formation in a series, rather than in a single uniform sheet, so that overlapping partial veils move in and out of the direct line of sight. The timing of the inner infrared brightening relative to the optical decline suggests that grains form very near the condensation radius, at a distance where radiation heating is strong enough to keep them warm for a short time, before drift carries them outward and cooling sets in. The observed lag between the deepest optical dimming and the mid-infrared peak spans only weeks to a few months, matching the travel time at measured wind speeds and linking geometry to motion. When the line of sight clears, brightness recovers, but color does not snap back immediately. A small residual reddening persists, implying that while the densest part of the clump or sheet has passed, a diffuse train remains shading the photosphere by a modest amount until it disperses. The event includes a temporary change in the appearance of molecular bands in the red and near infrared, with some bands deepening slightly. This behavior fits the picture of an outer atmosphere that becomes cooler or more extended for a time, altering the path lengths and temperatures where molecules form and survive. Radio continuum levels remain broadly consistent with expectations for a dense, slow wind, though small changes within uncertainties are reported during the optical minimum. If present, these changes may reflect altered ionization conditions near the star during the dust-forming interval, rather than a large shift in the ionized mass flux. High-cadence spectroscopy during the descent captures wave-like motions in the outer layers. Line cores shift back and forth by small amounts over periods of weeks, and weak emission components appear and fade near systemic velocity. Such patterns are a familiar sign of large-scale convective and pulsational dynamics in very extended atmospheres and provide a natural driver for episodic ejection of denser gas parcels that later seed dust. Imaging at visible wavelengths shows no dramatic new structure at the star's position, because the dust lies below the resolution limit during the event, yet difference images confirm that the change is localized and not a product of background fluctuations in the crowded field. In the infrared, the global shape of the halo does not alter on these short timescales, but the inner brightness profile steepens as expected when a new warm component arrives close to the star. The depth and duration of the minimum place bounds on the column density of dust added along the sightline. By adopting standard grain properties for oxygen, rich outflows, and by fitting the color change with a simple extinction law, modified by scattering a column, corresponding to a small fraction of a millimeter of solid material spread over a square meter, at the observer's distance emerges, which translates back to a compact clump or sheet of grains with a total mass, small compared to the full envelope yet large enough to alter the view dramatically for a time. The event does not require an exceptional change in the star's intrinsic luminosity. Rather, it arises from geometry and local chemistry near the condensation front, and it slots naturally into the broader outflow history in which the baseline mass loss carries a gentle stream outward, while surface motions and shocks occasionally trigger more efficient dust production. Seasonal monitoring shows that after the recovery, the star's brightness does not lock to a single value, but continues to vary on the familiar semi-regular timescales seen before the dimming with amplitudes typical of large convective cells and atmospheric motions in cool hypergiants. This continuity argues that the great dimming is not a step into a different evolutionary phase, but a pronounced expression of processes that operate at lower amplitude during quieter times. The distribution of polarization angle during the event hints at a symmetry in the inner dust, because the angle drifts rather than staying fixed, as would be expected for a uniform spherical shell. This drift suggests that the fresh dust is concentrated over a sector of the sky, as seen from the star perhaps associated with a single, long-lived upwelling on the surface, or with the convergent zone between adjacent convective cells. The observed wavelength dependence of the extinction during the minimum deviates mildly from the standard interstellar curve, consistent with somewhat larger grains than typical diffuse interstellar dust, or with a different mixture of grain shapes. Such differences are common in circumstellar shells where growth conditions select sizes and structures, unlike those found in the general interstellar medium. When the inner dust cools and moves outward, the mid-infrared excess relaxes and the color returns toward pre-event values, and the star's visible flux climbs toward its earlier mean. The echo of the event remains in the inner brightness profile of the infrared halo for a time, and in the placement of the most recently formed shell which joins the series of layers described earlier. The great dimming sits within a wider context of transient obscuration events seen in other luminous cool stars broadly similar in light curve shape and color behavior. The common pattern emerges from the shared physics of extended atmospheres, shocks grain nucleation and slow winds. In this case, the well-sampled photometry and spectroscopy allow a clear chronology that begins with strengthening asymmetric line profiles, and increasing color moves through a deep optical minimum with enhanced polarization, and a mid-infrared rise and closes with a steady recovery that leaves a new inner dust layer in place. With this sequence, the circumstellar environment records the event, both in the light that passes through it and in the material it adds to the envelope. High angular resolution observations bring the luminous cool hypergiant into view, not as a uniform circle of light, but as a resolved irregular source whose measured size and shape depend on wavelength and time. And this view arises through optical and infrared interferometry, where light collected by separated telescopes combines to sample fine spatial details far beyond the reach of a single mirror. The core product of such measurements is the visibility curve, a number that starts near unity on short baselines, where the source looks almost point-like, and then falls as the baselines lengthen and the instrument begins to resolve the disk. For an ideal, perfectly round, uniformly bright star, the curve follows a smooth known form, but in the case of this hypergiant, the measured visibilities depart from that template, and the departures signal a photosphere that is limb-darkened, extended and asymmetric. Fitting simple models provides a first step. A uniform disk fit gives a reference angular diameter, while a limb-darkened disk which allows the edge to fade, relative to the center, yields a slightly larger and more realistic scale. Elliptical fits test whether the apparent shape stretches along one axis, and these often improve the match to the data, implying that the photosphere, or its overlying layers, present different extents in different directions. Closure phases, which measure the degree of asymmetry without contamination from atmospheric phase, noise deviate from zero, indicating that the brightness distribution is not mirror symmetric. Such non-zero closure phases are common signatures of large convective cells, bright or dark patches, or localized dust scattering close to the star, and they reinforce the picture drawn from visibilities that the surface is not smooth. Multi-wavelength interferometry sampling near infrared bands where the star is bright and extinction is lower shows that the apparent size changes with wavelength, usually growing at longer wavelengths, where molecular layers and extended opacity contribute. This behavior tells that the interferometer is not viewing a sharp surface, but a fuzzy photosphere, plus outer molecular layers, sometimes called a molecular shell, which adds height to the apparent edge and shifts the effective radius outward. Spectrally dispersed instruments take this further by measuring angular size across narrow channels, centered on individual lines and on nearby continuum. The star appears larger in lines formed above the photosphere and smaller in adjacent continuum, and the difference maps the vertical structure of the outer atmosphere, offering a direct way to gauge how far those layers sit above the continuum-forming region. Over multiple epochs, the fitted diameters change by a few percent to tens of percent, which exceeds the differences expected from measurement error, and points to real evolution in the brightness pattern and in the height of the outer layers. These changes correlate loosely with phases of photometric variability and with episodes of stronger outflow traced by spectral lines, suggesting that the photosphere and the base of the wind respond together to the same convective and pulsational drivers. Image reconstruction applied when the interferometer collects enough baselines, and position angles produces two-dimensional maps that, while limited by sparse coverage, consistently hint at box-like or clover shapes rather than perfect circles. Bright sectors and dimmer wedges appear and shift between epochs, and the overall footprint sometimes stretches along a preferred axis, consistent with an oblate or tessellated outline rather than a smooth sphere. The box-like appearance has a natural explanation in the presence of large convective cells that inflate the atmosphere unevenly and in radiative transfer through a patchy molecule-rich layer that can sharpen corners where optical depth gradients align. In addition, scattering by nearby dust can add diffuse light along certain directions, altering the perceived limb and making edges appear flatter in projection. Calibrated position angles of the elongation remain similar within uncertainties across some observing seasons, hinting at a quasi-stable orientation for the larger scale structure, while smaller bright spots come and go on shorter timescales, pointing to a hierarchy of motions from global distortion down to cell scale flows. The measured angular diameters translate into physical radii only after adopting a distance and an effective temperature to locate the continuum-forming layer. Within distance ranges supported by photometric and astrometric studies, the resulting radius spans from about 1,000 solar radii to nearly twice that number, and the epoch-to-epoch changes imply that part of the variation in published radii arises from real-time dependent changes in the layers that set the interferometric edge. Limb darkening coefficients inferred from the fits align with expectations for cool extended atmospheres where temperature declines outward, yet they also vary across wavelengths and epochs in a way that again points to evolving molecular opacity and to temperature inhomogeneities across the disk. The combination of non-zero closure phases and wavelength-dependent size changes argues that some of the apparent asymmetry comes from hot or cool patches on the surface, rather than solely from a global ellipsoidal distortion. Radiative hydrodynamic models of very luminous low-gravity envelopes predict a handful of giant cells that move slowly and drive shocks into the overlying layers, and the interferometric data fit neatly into that framework by requiring only a few zones of enhanced or diminished brightness to explain the observed signatures. Photocenter shifts measured as wavelength-dependent offsets in the apparent position of the source reveal that line-forming regions can be displaced relative to the continuum center, a sign of outflow or infall superposed on lateral brightness gradients. These shifts remain small in absolute angular units, yet matter for precise astrometry, and provide a direct probe of gas motions very close to the star. When combined with contemporaneous spectroscopy, the interferometric maps help disentangle where specific lines arise. Lines that show deep P Cygni absorption are sensitive to the outward moving gas along the line of sight, while lines of molecules that form in cooler off-limb layers trace an extended ring that the interferometer resolves, and the difference between the two pictures clarifies both geometry and kinematics within only a few stellar radii. Reconstructed images also show hints of faint halos, just beyond the sharpest drops in visibility, which can be modelled as scattered light from dust at radii, not much larger than the condensation threshold. This component dilutes contrast and raises the fitted diameter, unless explicitly included, so careful modelling separates the compact photospheric light from the near-circumstellar contribution, preventing an overestimate of the true continuum radius. Temporal baselines spanning several years reveal that the orientation of the elongation and the location of bright sectors drift slowly with characteristic times compatible with the turnover of giant convective cells in a star of this size and temperature. Changes faster than a few months are rare at these scales, while finer substructures may evolve more quickly but remain at the edge of current imaging capability. Uncertainties in the absolute calibration of visibility and closure phase translate into bands of allowed models, rather than single unique maps and different regularization choices in the image. Reconstruction can emphasize either smoothness or compact features. However, the repeated finding of asymmetry, limb-darkening wavelength, dependent size, and time variation is robust against these technical choices. In practical terms, the interferometric view anchors the notion that the photosphere is extended, structured, and dynamic on humanly accessible timescales, and that the base of the wind sits close enough to influence the measured edge. Thus, the measured angular diameter is not a static property, but a snapshot that includes the porous molecule, rich layers above the continuum, and the imprint of large cells and nearby dust. Comparing epochs ties those snapshots into a sequence that tracks how the surface and its immediate surroundings rearrange as outflow waxes and wanes. Above the resolved photosphere stretches an outer atmosphere so extended that the idea of a single surface gives way to a layered volume where gas cools heats and moves under weak gravity. Strong radiation and the push and pull of large cells. Temperature drops outward from the continuum forming depth into molecule-rich strata, then rises locally where shocks pass while densities fall enough that collisions no longer dominate every process. In this region, molecules like carbon monoxide, water, and titanium oxide form and survive in cool pockets, imprinting broad bands on the spectrum and adding opacity that lifts the effective height where light escapes. These molecules assemble most easily in gas that has been lifted by pulsation or convection, cooled by expansion, and shielded by existing dust, or by overlying layers from the full glare of the photosphere. Giant convective cells extend from below the visible edge upward into this atmosphere, and their slow overturning drives vertical motions with speeds of several kilometers per second. Combined with global pulsation, these motions set up shock fronts that travel outward, compressing and heating gas for a short time before it cools behind the front and settles into a denser, cooler post-shock layer where molecules can reform. The sound speed at temperatures of only a few thousand degrees Celsius is itself only a few kilometers per second, so measured macroturbulent widths of 10 to 20 kilometers per second indicate supersonic conditions in places compatible with shocks strong enough to loft gas above the photosphere to radii where gravity no longer binds it tightly. In this levitated zone, the pressure scale height grows to a meaningful fraction of the radius, and the density gradient softens, allowing extended molecular layers, sometimes called a molecular shell, to form and persist. Interferometry senses these layers as a larger apparent size in bands dominated by molecular opacity, and spectroscopy reads them as deep bands whose strengths vary with time as the balance of heating, cooling, and lifting changes. Ionization in the outer atmosphere remains partial, and that opens pathways for magnetically guided waves to contribute energy and momentum. While large-scale ordered fields appear weak, even a gentle field can guide motions over many scale heights, and the coupling between ions and neutrals allows slow drifts that separate chemical species and influence where molecules condense. Microturbulence, a measure of small-scale chaotic motion, reaches several kilometers per second and broadens lines formed in these layers. Macroturbulence reflecting larger scale flows smears emerging radiation over tens of kilometers per second, so that line profiles become blends of thermal turbulent and bulk motions that shift as the atmosphere breathes. Radiation from below interacts strongly with the outer atmosphere through millions of spectral lines. Line opacity blocks and redistributes photons, heating upper layers where absorption dominates and cooling them, where scattering sends energy away, creating a patchwork of thermal conditions that varies with depth and angle across the disk. Where shocks push gas outward, density rises for a time, and the increased collision rate opens reaction channels that are closed in thinner gas. Molecules then form in abundance, and in cooling, they radiate further, lowering local temperature until the zone becomes a nest where dust seeds can appear if key species are present. The transition from pure gas to gas plus dust begins in the outer atmosphere, when small clusters of atoms assemble into the earliest grains. Once formed, these grains absorb the star's light and exchange momentum with the gas through collisions, increasing the outward acceleration and closing a feedback loop in which levitation by shocks places gas where dust can form, and dust once present helps carry the material farther out. The time between the passage of a shock and the appearance of dust depends on density and temperature. In denser parcels, the lag is short and near infrared. Colors register the arrival of new warm dust within weeks to months, while in thinner parcels growth stalls, and the layer remains molecular but dust-poor. Spectral diagnostics underline this cycle. Low excitation lines strengthen when cool, dense post-shock layers dominate the line-forming region, while high excitation lines fade. Forbidden lines from low ionization species appear weak but measurable in emission, signaling thin hot patches where shocks or waves raise the temperature slightly above the mean. The cores of strong lines shift back and forth over timescales of weeks, as parcels move outward and inward with the breathing of the atmosphere, and the line bisectors show asymmetric shapes that change sign a hallmark of large convective cells whose upflows and downflows do not cancel perfectly over the visible disk. Occasionally the base of the wind reveals itself in pure scattering lines that show broad wings from moving gas, and the blue edges of absorption troughs chart the terminal speed of the flow as it accelerates from near the escape speed at the photosphere to the slower, dense wind farther out. The escape speed close to the photosphere is only of order a few tens of kilometers per second because the radius is vast and gravity at the surface is weak. This low gravity regime ensures that relatively gentle pushes from shocks and radiation suffice to lift gas, and it explains how the atmosphere can extend to many times the photospheric radius before merging with the wind. Temperature inversions can appear above the molecular layers where radiation deposits energy in strong lines, and where dissipation of turbulent motions adds heat. Such inversions remain patchy and time-dependent, and they coexist with broad cool zones where molecules and nascent dust radiate efficiently. The horizontal structure of the outer atmosphere matches the cellular pattern traced by interferometry at the photosphere. Bright upwelling regions correlate with outward motions and with shock emergence, while darker downwelling lanes correlate with inflow and with reduced molecular absorption. As these patterns migrate and change strength, the shell becomes lopsided in density and temperature, producing the asymmetric scattering and polarization signatures seen in photometry. Over several months, the pattern drifts with the turnover time of the larger cells, while smaller features appear and fade more quickly, but the global envelope remains extended and quasi-static on the scale of years, because the average outflow and gravity balance to maintain a steady background over which fluctuations ride. The outer atmosphere also participates in cycles that connect to the events of major obscuration. When a low-order pulsation phase and a favorable convective configuration coincide, a series of stronger shocks can levitate gas more efficiently for a season-increase molecule formation and raise the dust yield at the condensation front. The line profiles become more asymmetric. Low excitation lines deepen, and the near-infrared continuum brightens slightly as warm dust appears, while visible light dims along sightlines that cross the thickened layer. After the high-activity phase, the levitated gas drifts outward. The inner atmosphere relaxes and line profiles soften, but the newly formed dust continues to influence the radiation field and to shape where molecules survive. Cooling times in the post-shock layers are short compared with drift times, so the chemistry responds quickly to the passage of shocks and can toggle between atom-dominated and molecule-dominated states within weeks. This responsiveness means that the spectrum serves as a near real-time monitor of the deep atmospheric motions that cannot be spatially resolved directly except by interferometry. The combination of weak gravity, strong radiative coupling, and large convective cells sets a boundary condition for the wind gas leaves regions where the radiative acceleration on dust and lines exceeds gravity stalls, where those forces balance and recirculates or falls back where support fades. The outcome averaged over angles is an outward flow whose speed and density match the rates measured farther out, while local departures form clumps and sheets that seed the structure of the circumstellar shell. At the largest radii still considered part of the atmosphere rather than of the wind, the gas becomes nearly ballistic, and its subsequent fate then depends on collisions, radiation pressure on grains, and mixing with earlier ejecta. All of these processes imprint themselves on the emergent spectrum, on the measured angular size in molecular bands, and on the time-dependent polarization of scattered light. And together they define the living outer layers that bridge the photosphere and the circumstellar envelope already described. The wind rises from the outer atmosphere as a slow, dense outflow that begins where gas lifted by shocks and large cells meets radiation acting on newly formed dust, and the physics of that launch explains both the measured speeds of only a few tens of kilometers per second and the high mass flux that builds the envelope. In the cool layers just above the photosphere line, driving on atoms and ions contributes less momentum than in hot stars because many lines saturate, and because ionization is low, so the first step is mechanical pulsation, and convective shocks lift parcels to radii, where temperatures fall, and molecules and small solid clusters can assemble. Once even a small fraction of condensates appears, radiation pressure on grains becomes effective because the star's peak output arrives at wavelengths where silicate and related materials absorb strongly. Those grains intercept photons, gain outward momentum, and share it with the gas through collisions, so the mixed flow accelerates gently and maintains density because gravity is weak at such large radii. The outflow's terminal speed reflects the balance between radiative push and gravitational pull, after allowance for energy lost to dust cooling and work done against pressure gradients. Because gravity scales inversely with radius, and the radius is vast, the escape speed at the base of the wind is of order only a few tens of kilometers per second, which matches the observed end speeds inferred from the blue edges of absorption troughs in wind-sensitive lines. Where dust abundance increases, acceleration rises, and the density profile steepens, but growth is not uniform in angle or time, so the wind inherits clumping from its launch region, with dense knots and sheets embedded in a smoother background. Opacity sits at the center of how this wind shapes apparent brightness, because it controls which photons escape and which are scattered or absorbed and re-emitted at longer wavelengths. Close to the star, where optical depths in molecular bands and dust continua become significant. Along some sight lines, the visible flux declines and reddens while near and mid-infrared flux grows. Small changes in where dust forms or in how it piles up can therefore modulate brightness without requiring a change in intrinsic luminosity. Scattering adds another layer of effect grains comparable in size to the wavelengths of visible light, scatter it efficiently and preferentially at forward angles. So when a clump crosses the line of sight, more of the observed light arrives by scattering from near the limb, and less arrives directly from the photosphere. Polarization rises during such passages, and limb darkening appears enhanced because the central rays suffer greater extinction than oblique paths that skim the edge and emerge after fewer interactions. The wind's temperature structure follows from radiative heating of dust and gas balanced against cooling by line emission and by grain radiation. Near the condensation front, grains remain warm at temperatures of a few hundred degrees Celsius and contribute a bright inner component to the spectral energy distribution, while farther out they cool toward tens of degrees Celsius, and the wind becomes nearly isothermal in the gas, because collisions with grains and radiation fields stabilize the temperature. The density profile roughly follows an inverse square law beyond the acceleration zone if the mass loss rate stays steady and the speed approaches a constant value. But departures arise from time-variable launch conditions and from instabilities in the expanding shells that concentrate matter into arcs and knots. Those concentrations raise local optical depth and produce the beaded rims seen in mid-infrared images, and they also bias mass loss estimates derived from any tracer that scales nonlinearly with density. Gas chemistry evolves along the flow. In the inner wind, molecules form and self-shield, and grain growth proceeds by addition of atoms and small clusters. Farther out, the radiation field weakens and collisions become infrequent freezing compositions into whatever mix was set near the base. If shocks propagate into the inner wind from renewed surface motions, they can reheat and partially evaporate grains at the condensation front, resetting growth and injecting fresh small particles that alter opacity and scattering properties for a time. The coupling between grains and gas depends on relative drift speeds and on charge. In denser zones, collisions keep drift low, and the two components move together, while in thinner regions, grains can pull ahead slightly, until drag re-establishes balance, a process that broadens the shell and smooths small-scale structure. The total momentum carried by the wind must come from the radiation field, and a simple check of momentum balance compares the wind's mass flux times terminal speed to the star's luminosity divided by the speed of light. Observed rates and speeds require multiple interactions between photons and grains, or a high mean opacity in the absorbing band's conditions that are met when dust is abundant near the launch zone, and when scattering redirects photons through the envelope instead of letting them escape immediately. Changes in opacity therefore regulate not only brightness, but also dynamics. When dust production rises, acceleration strengthens, the inner density grows because gas spends more time at low speed near the base, and the line of sight becomes more opaque, particularly in the blue where grain absorption is strong. When production falls, the wind becomes more transparent. The inner profile shallows and visible light recovers. Radiative equilibrium establishes a radial temperature gradient in dust that sets where different grain species contribute most. Silicates dominate at intermediate radii while cooler species emit beyond, and this stratification imprints broad features on the mid-infrared spectrum whose relative strengths shift with time as the inner geometry evolves. The gas responds by adjusting ionization and excitation conditions, so that emission and absorption lines of low ionization metals deepen when dense zones form and weaken when the wind thins. Because gravity is low, the wind remains only weakly bound to stellar rotation or large-scale magnetic fields, yet even mild rotation can imprint a subtle equatorial enhancement. If centrifugal support reduces effective gravity at low latitudes, and a gentle field can guide flows enough to elongate the inner envelope. Such shaping would modulate opacity with angle and contribute to the asymmetric brightness profiles inferred from polarization and interferometry. Observed terminal speeds of only a few tens of kilometers per second imply that the wind is momentum-driven rather than energy-driven. There is no need for a hot-fast component as in the winds of hot luminous stars, and the lack of strong X-ray emission from shocked fast gas supports the picture of a cool, slow flow dominated by dust-mediated acceleration. In lines that sample different depths, profile shapes change from pure absorption close to the star to P Cygni forms, where scattering in the accelerating region fills in the red wing and erases part of the blue emission. The progression maps the run of velocity and optical depth, and confirms that acceleration happens within only a few stellar radii above the photosphere. Farther out, where speeds settle, line widths narrow, and centers drift toward the systemic velocity, while the continuum from dust transitions from a warm shoulder to a broad, long wavelength excess. All of these signatures feed back into estimates of stellar parameters because extinction and scattering shift the observed colors and dilate the apparent angular size. If not accounted for, the star seems cooler and larger than the continuum-forming layer alone would indicate, and its inferred luminosity shifts accordingly. Correcting for wind opacity requires multi-band fits that include a radiative transfer model for the envelope and care with geometry, since a symmetric assumption can under- or overestimate the column density along the actual line of sight when clumps or sheets intervene. With such corrections, brightness variations align with phases of dust production and redistribution, rather than with large excursions in intrinsic power, and the wind emerges as the principal modulator of what an observer sees on seasonal timescales. The light that leaves the hypergiant carries a layered signature, and its spectrum changes with time in ways that match semi-regular variations in brightness and colour. So observers read both the detailed lines and the slower rhythms to estimate temperature, gravity, and the state of the extended atmosphere. At high resolution, the visible spectrum shows a dense forest of lines from neutral and singly ionized metals, with strong features of iron, titanium, and calcium that deepen when the outer layers cool and lighten when they warm. The near-infrared adds the prominent triplet of singly ionized calcium, whose depth correlates with low surface gravity, and with the pressure-broadened wings expected in an extended photosphere. Hydrogen lines vary from season to season with the Balmer-alpha transition, alternating between deep absorption and complex profiles that include emission wings or P Cygni shapes. These forms trace the base of the wind and the passage of shocks through the upper photosphere, and their blue edges mark shifts in the terminal speed by a few kilometers per second. Sodium doublet lines appear broad and structured with superposed narrow components from interstellar clouds along the line of sight and a wider stellar component that responds to changes near the photosphere. The interstellar features remain fixed while the stellar core breathes with the atmosphere and grows asymmetry during episodes of stronger outflow. Molecular bands of titanium oxide and water deepen when the effective temperature dips into the regime associated with very cool supergiants, and they weaken when the temperature climbs toward the late G boundary. This modulation, together with the behavior of metal lines, explains why classifications in the literature span late G to early M, because the mean temperature hovers near the crossover, while time-dependent layers add or remove opacity. In the red and near-infrared bands of carbon monoxide appear in vibration rotation, absorption, their depth indicating cool layer column density above the continuum-forming region. These bands track with near-infrared colors and brighten gently when levitation lifts gas and cooling follows behind shock passage. Forbidden lines of low ionization species, including weak emissions from neutral oxygen and singly ionized calcium, show up at some epochs as narrow, low-contrast features that form in thin hot patches where density is low. Their presence demonstrates that the atmosphere and inner wind include zones where cooling leaves gas near the conditions needed for forbidden transitions, though they remain subdominant compared with the strong permitted lines. Diffuse interstellar bands pepper the spectrum as broad absorptions of unknown molecular carriers and help calibrate the total reddening toward the star. They serve as background markers that do not vary with the stellar cycle and anchor corrections for extinction when colors change during dust-forming episodes. Radial velocity curves derived from numerous metal lines reveal semi-regular patterns with characteristic times of several months to about a year, a range familiar from other luminous cool stars with large convective cells. The amplitudes remain modest of order a few kilometers per second, but the phase relationships between lines formed at different depths show that the outer layers lag behind deeper layers, consistent with upward propagating disturbances. Line bisectors bend one way during rising light, and the opposite way during decline, indicating that the field of upflows and downflows across the disk changes its balance as the atmosphere breathes. This change also drives small photocenter shifts measured interferometrically across specific lines linking spectroscopic and spatial diagnostics. Photometric monitoring in standard bands records a mixture of short and long characteristic times. A shorter timescale of several tens of days appears in small amplitude undulations that likely trace local cell evolution, while a longer timescale on the order of a few hundred days marks global breathing, in which temperature and radius both drift slightly, changing the bolometric correction and pushing the color along the locus expected for a reddening-free change in temperature. Superposed longer drifts reflect cycles of dust formation that alter extinction and scatter light across bands. The amplitude in visible light reaches roughly a magnitude during extreme obscuration events, but more typically stays within a few tenths of a magnitude across ordinary seasons. Color changes follow a pattern in which the star reddens as it dims during dust episodes and moves along a shallower color path during purely photospheric cycles, allowing the two influences to be separated statistically over long baselines. Effective temperature estimates thus depend on phase and on whether circumstellar veiling contributes along the line of sight. When the inner dust layer is thin and scattering small spectral fits to metal line ratios and molecular band depths, place the temperature near the boundary between late G and early K. When dust thickens, or the outer layers cool, molecular bands deepen, and temperature estimates shift toward early M, and the derived radius and luminosity adjust accordingly when the spectral energy distribution is refit with updated extinction. Bolometric luminosity remains the most stable parameter, because integration across wavelengths compensates for band-specific shifts, but even that value inherits uncertainty from distance, and from the fraction of light redirected by scattering rather than absorbed and re-emitted in the infrared. A practical approach combines multiband photometry, high-resolution spectra, and near-infrared fluxes to build spectral energy distributions at many epochs, then fits them with radiative transfer models that include a photosphere molecular layers and a thin dust shell. These fits return temperatures that move within a few hundred degrees Celsius around a mean reproduced line depths and colors and match the mid-infrared excess when warm dust is present. The solution set is not unique because clumping and geometry alter the path length through absorbing layers, but the range of temperatures required falls squarely in the late G to early M zone, a span fully compatible with a very cool, very extended hypergiant. Power spectra of long light curves show broad peaks rather than sharp lines, a hallmark of semi-regular behavior driven by overlapping processes rather than strictly periodic pulsation. The width of the peaks reflects the wandering of cycle length as convective cells evolve, and the relative power in different bands indicates that temperature changes dominate short timescales, while extinction changes dominate the slowest drifts. Cross-correlation between color and radial velocity curves places velocity maxima near times of rising light, when upflows expand the atmosphere and reduce line blanketing, and places velocity minima near declining light, when downflows increase density and deepen metal lines. The lag between these signals remains stable over several years, supporting the picture of upward propagating disturbances that begin near the photosphere and move outward into the molecular shell. Spectral diagnostics that isolate gravity, such as the wings of strong metal lines, confirm extremely low surface gravity when modelled with extended atmosphere calculations. Those wings broaden and shallow in concert with photometric cycles, implying small radius changes that nonetheless modify pressure stratification enough to alter line formation depths. The near-ultraviolet, where metal line blanketing ordinarily hides the continuum, becomes especially sensitive to small temperature shifts in such cool stars. When the atmosphere warms by a few hundred degrees Celsius, the blanketing weakens, and the near-ultraviolet flux rises disproportionately, while during cooling phases the flux collapses back and the continuum disappears below the forest of lines. In the mid-infrared, the spectrum shows wide silicate features whose strengths rise and fall with the production and temperature of grains. Their temporal behavior lags optical cycles by weeks to months, consistent with the travel time from the molecular shell to the condensation radius, and this lag serves as a yardstick for distances within the inner envelope when combined with measured wind speeds. Together, the line profiles band strengths, color curves, and radial velocities sketch a portrait of a star whose effective temperature strolls across the late G to early M boundary, whose spectrum breathes as layers lift and settle, and whose brightness reflects both photospheric change and the veiling of dust. The variability is semi-regular rather than strictly periodic, with nested timescales from weeks to more than a year, and every diagnostic points back to the same physical stage, a very extended low-gravity photosphere overlain by molecule-rich layers and coupled to a slow opaque wind. Estimates of size and power for a very luminous, cool hypergiant rest on three pillars that must be balanced at the same time: angular diameter, on the sky distance through the spiral arm, with its heavy extinction and effective temperature that sets how much light each square meter of the surface emits. Uncertainties in any one of these propagate into the others, so ranges rather than single numbers provide the honest description. Angular diameter comes from interferometry and shows a photosphere that appears larger at wavelengths where molecular layers add opacity and smaller in adjacent continuum windows. Fits to limb-darkened disks and asymmetric brightness maps give diameters that change by several percent to tens of percent across bands and between seasons, reflecting not just measurement error but real changes in the height of molecule-rich layers and in the pattern of bright and dark surface patches. Distance enters through astrometry and through associations. Parallax for such a bright reddened and resolved source can suffer from systematics tied to calibration and to wavelength-dependent photocenter shifts, so the formal solution must be widened by realistic error flaws. Kinematic distances inferred from line velocities along the spiral arm require careful modelling of non-circular motions and carry their own biases, and photometric distances built from cluster sequences or from the star's spectral energy distribution demand extinction corrections that vary across the field and within the circumstellar shell. The outcome is a bracket rather than a point distances cluster, within a range compatible with the Perseus arm segment in Cepheus, and overlap with values quoted for nearby clusters and associations, but the span remains wide enough that physical radius and luminosity carry factors of order 2 in their allowed intervals. Temperature completes the triad, spectral fits that account for extended atmospheres, and for the veiling from near stardust. Place the effective temperature within a band running from late G to early M classes, which in physical terms means a surface at a few thousand degrees Celsius that wanders within several hundred degrees over semi-regular cycles. The near-ultraviolet becomes a sensitive lever, because small temperature lifts weaken line blanketing and raise the flux, while the red and near-infrared respond through molecular band depths that deepen in cooler phases and relax when the surface warms. With an angular diameter, a distance, and a temperature, the physical radius follows from simple geometry, and the luminosity from the Stefan view of radiant power, but each inherits the combined uncertainty. Using continuum-weighted diameters rather than molecular band-inflated values, and adopting the distance intervals supported by astrometry and association arguments, the radius lies around about 1,000 solar radii in the compact end of the allowed space and approaches nearly 2,000 solar radii at the extended end, with epoch-to-epoch changes of a few percent to perhaps a tenth, reflecting the shifting outer layers that the interferometer senses. The corresponding bolometric luminosity, after integrating a spectral energy distribution that includes visible near-infrared and mid-infrared bands, with a correction for circumstellar re-radiation spans from several 100,000 times the power of the Sun to more than 1,000,000 times, with the lower end favoured when distance and temperature sit at the small and warm side of their ranges, and the higher end favoured when distance and diameter sit at the large side and temperature at the cool side. Extinction toward the star divides into a steady interstellar component and a variable circumstellar component that thickens during dust-forming intervals. The first is estimated from diffuse interstellar bands, from colours of nearby early-type stars, and from three-dimensional dust maps of the arm, while the second is constrained by the colour changes and polarisation during dimming events, and by the mid-infrared excess from warm near-star grains. Errors in the total extinction fold directly into luminosity because they set how much flux must be added back to account for absorbed light. Underestimating extinction yields too small a luminosity, while overestimating extinction yields too large a luminosity. Scattering complicates this step further by redirecting some optical photons rather than absorbing them, so a portion of the missing visible flux emerges as polarized scattered light, rather than as mid-infrared re-radiation. Radiative transfer models that include both absorption and scattering recover more reliable bolometric corrections, and narrow the luminosity band by acknowledging that not all dimming is pure absorption. The angular size used in radius calculations must match the layer that emits most of the bolometric flux. Using a diameter measured inside a molecular band that forms above the continuum would overstate the true continuum radius, while using a pure continuum window that is not contaminated by molecular opacity gives the better scale. Multi-wavelength interferometry helps by delivering diameters across many channels, allowing a selection of those that track continuum best. Remaining asymmetry then introduces scatter, because a limb that is brighter along one direction can bias fits that assume symmetry, yet closure phase informed image reconstructions allow ellipticities and brightness sectors to be included and reduce that bias. Distance systematics can be mitigated by cross-checks. If the star truly belongs to a nearby compact cluster, or to a well-defined subgroup of the loose association, then the distance to that group offers an anchor independent of parallax. Conversely, if proper motion or radial velocity disfavors bound membership, then the parallax takes primacy, and the photometric comparisons to the group become context rather than constraint. In practice, the distance range that survives these cross-checks still spans a significant fraction of the absolute value, and that span remains the dominant contributor to the luminosity range, while temperature uncertainty shifts the luminosity by a smaller factor through the bolometric correction and through small changes in the chosen continuum diameter. The spectral energy distribution ties the pieces together. In seasons without heavy obscuration, visible and near-infrared fluxes shape the photospheric peak, while mid-infrared points catch the warm dust shoulder. In seasons following a dust event, the mid-infrared brightens and the visible dims, but integrating over the full wavelength range recovers a bolometric flux that varies less than any one band alone, consistent with the view that the star's intrinsic power moves only slightly while circumstellar opacity and geometry redistribute the light. Fitting many epochs with the same distance but with temperatures and extinction, allowed to vary within observational limits, yields a stable mean luminosity with slow drift and with excursions during the deepest obscuration. Repeating the exercise across the distance bracket expands the mean upward or downward, but preserves the pattern of modest intrinsic variability. Radius estimates carry two further subtleties. First, the photosphere of such a star is porous and patchy, so the concept of a single sharp surface becomes a wavelength-dependent average. Second, the molecular shell adds height in some directions and at some times, and even with careful band selection, the measured radius represents an optical depth contour rather than a hard boundary. These facts argue that quoted radii should be understood as effective radii tied to the chosen bands and epochs, and that differences between studies can reflect real atmospheric change as well as distinct methodological choices. Within these caveats, the picture remains that of an object whose size rivals or exceeds the orbits of the inner planets, if placed at the centre of the solar system, and whose power lies in the top tier of cool, massive stars known. The ranges matter for evolutionary inferences because in the Hertzsprung-Russell diagram, even a shift of a few tenths in luminosity or temperature can move the star between tracks, computed for different initial masses or for different mass loss histories. Acknowledging the full bracket keeps those inferences honest and motivates continued efforts to refine distance through improved astrometry and to refine diameter through longer baseline interferometry that isolates continuum. For present purposes, the combination of continuum angular sizes, conservative extinction corrections, spectral temperatures that average late G through early M behavior, and distance consistent with the Perseus arm delivers a radius of about 1 to nearly 2,000 solar radii and a luminosity of several 100,000 to above 1 million solar outputs with epoch-to-epoch shifts that reflect genuine changes in the extended layers that sit just above the continuum and not only measurement noise. Deep inside, the luminous, cool, hypergiant energy production continues in a compact core that sits beneath shells where earlier fuels still burn, and this arrangement sets the surface conditions seen today. The combination of very high luminosity and cool effective temperature places the star among the most inflated massive stars, where models typically locate the present stage in core helium, burning with the surrounding shell of hydrogen burning. In this configuration, helium fuses into carbon and oxygen in the core, through reactions that require temperatures of hundreds of millions of degrees Celsius, while just above the core a thin layer continues to convert hydrogen into helium through the catalytic carbon-nitrogen-oxygen cycle. Because the core carries most of the weight, it remains dense and hot, and contracts slowly as helium is consumed, and the energy that leaves the core and shell must cross a vast dilute envelope before it reaches the photosphere. The envelope is strongly convective. Opacity in cool, partially ionized hydrogen-rich gas is dominated by negative hydrogen ions, whose abundance depends on free electrons provided by metals. Where opacity rises with temperature, the radiative gradient steepens and convection turns on transporting energy outward in slow, deep cells that overturn on timescales of months to years. This convective transport imposes a near adiabatic temperature gradient through much of the envelope, fixing a relation between radius and effective temperature for a given luminosity. As a result, small shifts in the core or shell power alter the outer layers only modestly, while changes in opacity or density within the envelope can move the photosphere over a larger range. The hydrogen-burning shell acts like a thermostat that helps maintain the high luminosity. Whenever the envelope expands and cools slightly, the shell contracts minutely and heats, raising the local rate of hydrogen burning and boosting the outward flux. When the envelope compresses and warms, the shell relaxes and the rate falls. This feedback keeps the luminosity near a steady mean on seasonal timescales, which matches observations that the bolometric output varies less than individual bands affected by dust and molecular opacity. In the core, helium fusion proceeds in a non-degenerate plasma, unlike the lower mass red giants where electron degeneracy can support the core. Here, thermal pressure dominates, and the response to fuel depletion is a gentle contraction that increases central temperature and maintains a nearly constant energy supply as long as helium remains abundant. The stratification above the core carries chemical fingerprints upward through convection and wind. Material exposed to the carbon-nitrogen-oxygen cycle shows nitrogen-enhanced and carbon and oxygen-depleted abundances near the surface, a pattern frequently reported in luminous cool supergiants and hypergiants. The presence of such processing at the photosphere implies that convection or prior mixing and mass loss have dredged up inner layers consistent with a deep convective envelope powered by a bright core and shell. The radius owes its size to the balance between high internal luminosity and the low effective temperature set at the photosphere. With the envelope close to fully convective, the star inflates until the surface cools to a point where opacity falls enough to let the required flux escape. That point lies in the range from late G to early M class in agreement with spectral diagnostics. Because the escape of energy is regulated by envelope structure rather than by rapid core changes, the star's present variability arises largely from the envelope's response to small perturbations such as pulsation and cell evolution, rather than from large shifts in nuclear power. Pulsation links the interior to the observed surface motions through the period mean density relation. The semi-regular timescales of months to about a year match the long fundamental or low-order overtone modes expected for such an extended low-density envelope. These modes modulate radius and temperature slightly, and seed the shocks that rise through the outer atmosphere, assisting dust formation at the condensation front. The small amplitudes inferred from radial velocity curves and from modest changes in gravity, sensitive line wings align with this picture. The interior delivers steady power, and the envelope rings softly while carrying that power outward. Energy transport across the boundary from the hydrogen-burning shell into the base of the envelope includes a thin radiative zone in some models and becomes fully convective in others, depending on adopted opacities and mixing length. Either way, the transition occurs at depth far beneath the photosphere, and disturbances take significant time to reach the surface, smoothing any fluctuations produced near the core and shell. Neutrino losses at this stage remain a minor channel, compared with photon luminosity because helium burning temperatures, while high, have not yet advanced to the extreme regimes where thermal neutrino processes dominate. Thus, almost all of the nuclear energy emerges as radiation, and ultimately powers the star's light and wind. The mass of the convective envelope has been reduced by sustained mass loss. As material leaves through the wind, the outer boundary of convection moves inward in mass coordinates, making it easier for processed layers to reach the surface and changing the vibrational properties of the envelope. A lighter envelope over a bright core also means weaker gravity at the photosphere, which promotes larger-scale convective cells and supports the low terminal speeds measured in the wind. This coupling between energy source and outer structure helps explain why changes in dust and line-driven opacity near the photosphere can modulate brightness strongly while leaving total power nearly stable. The hydrogen and helium ionization zones inside the envelope play a further role. Partial ionization absorbs energy during compression and releases it during expansion, a mechanism that can feed pulsation in low-order modes and set preferred timescales. These zones also raise opacity, locally steepening the radiative gradient and reinforcing convection. The result is an envelope with built-in valves that convert steady core and shell power into gentle time-dependent motions that appear in line profiles, interferometric diameters, and photometric cycles. The chemical stratification above the core includes ashes from helium burning. Carbon and oxygen produced in the core do not yet reach the surface in large quantities, because a radiative layer and the hydrogen-burning shell form barriers to direct convective mixing. However, as the wind erodes the envelope and as mixing proceeds through slow processes like semi-convection, or rotationally induced shear traces can appear in the outer zones. Today, surface diagnostics emphasize carbon-nitrogen-oxygen cycle signatures more than core helium ashes, consistent with the phase where helium burning is ongoing in the center and hydrogen burning continues in a shell. The pressure and temperature structure also sets the base of the wind, where the convective flux hands off to radiation near the photosphere. Temperature gradients and densities determine the strength of acoustic and shock generation, while the outgoing radiative field shaped by the current effective temperature sets the momentum available to dust once it forms. The wind then feeds back on the energy balance by carrying away enthalpy and lifting material that cools and radiates in lines and continuum, but the power required remains a small fraction of the core and shell output, so the interior maintains its conditions without being drained by the outflow. Timescales inside and out differ by many orders of magnitude. Helium burning in the core proceeds over hundreds of thousands to a few million years for massive stars, whereas convective turnover and pulsation cycle in months, and dust formation waxes and wanes on similar short spans near the condensation radius. The large separation of timescales explains why the observed semi-regular variability can persist without signaling a change in the internal source. Presently, the energy budget is thus partitioned clearly. Nuclear fusion in the core and shell generates power, convection transports it through the envelope, and radiation and slow mechanical work by the wind carry it away from the photosphere. The modest amplitude of observed temperature swings the stability of bolometric flux across seasons compared with band-specific changes, and the abundance patterns at the surface all align with a star in core helium burning with an active hydrogen shell housed beneath a deep convective envelope that controls the visible state. The path that brings a very luminous, cool hypergiant to its present state, and that will carry it onward, is governed by initial mass rotation metallicity and mass loss, with the last of these acting as a lever that can redirect the track across the Hertzsprung-Russell diagram. The envelope's erosion by a slow dense wind reduces the weight pressing on the burning core and alters both surface gravity and opacity, which feeds back on temperature and radius. Models that begin with very high mass and near solar composition commonly evolve from hot compact main sequence stars through a bright supergiant stage into the cool inflated domain where a deep convective envelope forms. At this point, core helium burning stabilizes the luminosity, while hydrogen burning continues in a thin shell, and the star settles into the redwood reach of its loop. The next steps depend on how rapidly the envelope thins. When mass loss remains modest, the envelope stays heavy, convection remains deep, and the star lingers in the cool quadrant, showing semi-regular variability, molecule, rich spectra, and slow winds. When mass loss strengthens either through a sustained rise in the baseline rate or through repeated intense episodes, the envelope mass declines relative to the core. The ratio of luminosity to mass climbs, and the outer layers become more weakly bound, at a threshold that varies with composition and rotation. The star turns blueward, shrinking in radius and warming at the surface while maintaining a comparable bolometric power set by the burning interior. This blueward excursion can pass through temperatures where the opacity peak from iron group lines enhances radiative acceleration in the outer layers, promoting instability and outflow. Some tracks cross the domain of luminous blue variables, objects that show irregular eruptions, strong winds and spectroscopic changes as they hover near an opacity edge, while others move more directly toward hotter compact states as the envelope withdraws. Continued stripping exposes layers that have been processed by nuclear burning. First, the products of the carbon-nitrogen-oxygen cycle dominate with nitrogen enhanced, and carbon and oxygen depressed at the surface, a pattern already seen in the current cool phase. With further mass loss, helium-rich layers come closer to the photosphere, and if the hydrogen-rich mantle becomes sufficiently thin, winds driven by line opacity at higher temperatures can peel away the remaining hydrogen. At that point, a Wolf-Rayet-like phase can emerge, characterized by a compact radius, a very hot surface, strong broad emission lines from dense fast winds, and a chemistry that reflects deeper burning products. The timescale from the cool hypergiant stage to any hot-stripped phase depends on the balance between the pace of wind-driven erosion and the remaining lifetime of core helium burning. Stronger winds and higher luminosity to mass ratios favor more rapid blueward motion, while weaker winds and heavier envelopes permit longer residence in the cool state. Rotation weaves through this picture by mixing fresh fuel into the core and transported ash toward the surface, by flattening the star so that equatorial gravity is slightly reduced, and by promoting a mild equatorial density enhancement in the wind. These effects can lengthen core helium burning smooth gradients that would otherwise impede blueward evolution and imprint modest asymmetries on the envelope that persist into later phases. Metallicity sets the abundance of elements that provide free electrons and that carry line opacity. Higher metallicity strengthens line driving in hot phases and increases negative hydrogen opacity in cool phases, modulating both the wind and the envelope structure. Observationally, the present object already shows hallmarks of a trajectory biased toward eventual heating. Heavy mass loss over long spans, signatures of processed material at the surface, a polarized and asymmetric near-star environment that hints at organized outflow channels and interferometric elongation that may reflect weak rotation or residual shaping by magnetic fields and large cells. Yet the star remains cool today, which indicates that the envelope still carries substantial mass and that convection continues to regulate the outer structure. In tracks where the envelope contracts while luminosity stays high, the photosphere warms out of the molecule-rich regime into a line-blanketed continuum where ultraviolet radiation rises and where line-driven winds become more effective. As that happens, mass loss can accelerate, creating a feedback that hastens the exposure of deeper layers. In other tracks, the star may execute a small blue loop and return briefly to cooler temperatures if the envelope responds to changes in shell burning, or if opacity shifts with temperature in a way that reinflates the outer layers. Such loops remain sensitive to details of mixing semi-convection and the treatment of turbulent pressure, so different calculations present different amplitudes for the excursion. Regardless of the exact path, the core proceeds from helium burning toward heavier element fusion, as fuel is exhausted in the center and fresh stages ignite in shells. Each new stage contracts the core, raises its temperature, and once active supplies the outward power that the envelope must radiate. Because later burning stages occur at higher temperatures and shorter timescales, the outer appearance between them may not change dramatically if the envelope is already thin and hot, while in a still cool and massive envelope, the response can include modest radius and temperature shifts that alter spectral class without changing luminosity much. The mass loss history recorded in the circumstellar dust constrains viable tracks by demanding integrated losses large enough to have removed a significant fraction of the initial envelope. The far halo points to earlier strong phases that, added to ongoing shedding, bring the star closer to conditions where a bluewood turn becomes likely. When it begins, contraction of the outer layers elevates the effective temperature and reduces the optical depth in molecular bands, and the infrared excess from warm dust near the condensation front shrinks because the condensation radius shifts inward in physical units while the wind changes character. The transition in wind regime from slow dust-mediated acceleration to faster line-driven acceleration alters terminal speed and density profile, and the spectral diagnostics shift from molecular and low ionization metal lines to strong ultraviolet and optical emission complexes. In a population context, cool hypergiants occupy a narrow luminous swath above the standard red supergiant domain, and are often interpreted as waypoints for very massive stars that have already shed enough mass to lie near instability boundaries. Their rarity and the rich circumstellar structures they build support the view that they are brief, but influential in gas and dust feedback to their natal arms. As the present star continues to lose mass, the chemical horizon at the surface moves inward, revealing deeper processing and strengthening the evidence for interior burning stages, while the dynamics of the envelope edge and the efficiency of dust formation decide how long the star shows the cool skin that now defines it. Radii that span from about 1,000 to nearly 2,000, solar radii luminosities of several 100,000, to more than 1 million solar outputs and winds that carry matter outward at only a few tens of kilometers per second, describe a state close to the tipping point where a sustained increase in mass loss or a change in envelope opacity can redirect the track upward in temperature. Continued interferometric monitoring, multiband spectroscopy and infrared mapping of the inner dust will reveal whether the photospheric size contracts on multi-year spans, whether line profiles transition toward patterns typical of hotter winds, and whether the inner dust boundary migrates, all of which would mark the early steps of bluewood motion. The present evolutionary understanding thus frames a consistent sequence. A very massive progenitor evolves off the main sequence, inflates as envelope opacity and convection rise, establishes core helium burning with a hydrogen shell, sheds mass through a slow dense wind that imprints the surrounding halo, enriches its surface in nitrogen through mixing, and then when the envelope becomes light enough heats at the surface as the radius contracts, while luminosity remains high, passing into hotter, supergiant or luminous blue variable-like domains, and with further stripping approaching a Wolf-Rayet-like state. Timescales that govern a very luminous, cool hypergiant divide into families that operate from weeks to millions of years, and uncertainties arise because the signals from these families overlap, while observations sample only a fraction of the full span. The result is a picture with robust outlines and broad error bars, especially when translating observables into distances, radii luminosities and remaining lifetimes. At the shortest end-line, profile shifts, polarization changes and near-infrared color wiggles unfold over weeks, matching the turnover of large convective cells and the flight time from the photosphere to the condensation front at speeds of only a few tens of kilometers per second. These cycles set the cadence for dust nucleation bursts that modestly veil the star and that build the innermost warm shell. On scales of a few months to about a year, semi-regular photometric variations appear as the envelope breathes in low-order modes, and interferometric diameters drift by a few percent as molecular layers swell and subside. These motions are repeatable in character, but not in exact period or amplitude, so analysts describe them statistically rather than with a single clock. Over spans of several years to a decade, the inner dust geometry evolves as clumps drift outward and as new condensations add layers, producing slow changes in mid-infrared brightness and in the slope of the spectral energy distribution between near and mid-infrared bands. Because fresh events occur before older ones disperse, brightness and colour tracks reflect a superposition that resists clean isolation into single episodes. At the longest end, far-infrared halos record centuries of mass loss, and the cumulative dust mass implies that the star has spent a substantial fraction of its cool phase shedding matter at high rates punctuated by stronger intervals whose imprints now sit at large radii. Yet even this archive, though extended, carries ambiguity because interstellar filaments in the same arm emit in the same bands and can blend with the outermost circumstellar layers. The uncertainties begin with distance. Parallax for a bright resolved and variable source suffers from calibration systematics and from wavelength-dependent photocenter shifts that arise when line-forming regions are offset from the continuum center. Gaia-like solutions must allow flaws on formal errors and careful filtering of outliers, and the residual range in distance propagates directly into radius and luminosity. Kinematic distances computed from line velocities along the spiral arm require a model for non-circular motions driven by the bar and by local streaming. Modest deviations in the assumed flow translate into tens of % differences in line-of-sight distance, and patchy extinction means that a background object can masquerade as a nearer one if reddening corrections are applied with a generic law rather than with a locally tuned curve. Cluster anchoring helps only if membership is secure, and as discussed earlier, proper motions, radial velocities and reddening patterns do not yet lock the hypergiant to a single compact group. Thus, distance must remain a bracket that in turn widens radius and luminosity into ranges rather than points. Effective temperature estimates also carry structured uncertainty. Extended atmospheres with molecule-rich layers erase the idea of a unique photospheric temperature at a single depth. Different diagnostics weight different heights, and circumstellar scattering alters continuum slopes in the visible without adding equivalent thermal emission in the same bands. Metal line ratios, molecular band depths, and near ultraviolet blanketing each trace temperature, but their calibration relies on model atmospheres that assume spherical symmetry and adopt mixing length prescriptions for convection. The real star is patchy and asymmetric, so the derived temperature should be read as an effective mean that fluctuates by a few hundred degrees Celsius around a center value. Extinction splits into interstellar and circumstellar parts, and both vary with wavelength in ways that are not fully captured by a single law. Interstellar extinction curves along the Perseus arm differ from classical diffuse curves in the relative strength of the near-ultraviolet bump and in the steepness of the blue rise, while circumstellar grains grown in dense warm gas near the star can be larger and more irregular than diffuse interstellar grains, producing greyer extinction and stronger forward scattering. Using an interstellar curve for circumstellar dimming underestimates the role of scattering and can lead to inflated bolometric corrections, while adopting a grey circumstellar law for interstellar reddening can undercorrect visible colours and bias temperatures low. Geometry adds another layer of uncertainty, because clumps and sheets in the wind make extinction angle dependent. A single line of sight sampling a dense inner sector does not represent the global mean, and comparing seasons with different viewing columns can mimic luminosity change even when the bolometric power stays nearly constant. Interferometric diameters encode both continuum and molecular opacity, and respond to bright and dark patches across the disk. Model fits that assume axial symmetry can overstate or understate the true continuum radius depending on how the patchy limb projects onto the sparse baseline coverage. Closure phase informed imaging mitigates this bias, but image regularization choices and finite sampling leave families of acceptable maps rather than unique scenes. Translating any one map into a single diameter thus carries method uncertainty that should be included alongside measurement error. Mass loss rates inherit uncertainties from clumping grain composition and gas-to-dust ratio. Free radio emission scales with the square of electron density, and thus with the square of clump contrast, so a clumped wind appears brighter than a smooth wind with the same average mass flux. If clumping is ignored, the inferred rate rises above the true rate. Infrared dust emission depends on grain opacity and temperature, both uncertain in detail for silicate-dominated mixtures grown in oxygen-rich flows. If grains are larger, they radiate more efficiently at long wavelengths and require less mass to reach a given brightness, while if they are porous or coated, their opacities shift with wavelength. The gas-to-dust ratio often uses a standard value that may not apply in the immediate circumstellar environment, altered by enrichment and by chemistry, so rate conversions remain bracketed. Terminal speeds inferred from the blue edges of P-Cine absorptions require the continuum level to be defined against a changing and sometimes scattered background. Small misplacements of the continuum yield kilometer-per-second shifts that affect travel time, estimates between the condensation front and the inner halo, and those shifts propagate into the time mapping used to connect light curve lags with physical radii. When these measurement families feed into evolutionary timescales, the uncertainty widens further. The duration of the cool hypergiant phase depends on current mass-remaining envelope mass and the competition between core helium burning time and the rate at which winds strip the mantle. Present mass is not measured directly, and envelope mass must be inferred from a combination of surface gravity radius and evolutionary tracks that themselves depend on mixing and rotation prescriptions. If the star began life very massive and has already shed a large fraction of its envelope, then only a modest further loss can drive it blueward within a timescale, short compared with the helium-burning clock. If the envelope remains heavy, it can linger in the cool state longer. Observations tell that mass loss has been high for at least decades and likely centuries, but they do not uniquely determine the integrated loss needed to reach the bluewood threshold. Predicting an end-of-life date is therefore not possible with present data. Even if the blueward turn begins later, burning stages proceed ever faster, but they unfold mostly at high temperature and deep inside decoupled from the slow outer response as long as an extended envelope persists. As a result, surface diagnostics provide only loose constraints on the internal countdown during the cool phase. What is known securely is the ordering of timescales, weeks for shock passage and dust growth near the condensation front, months for convective turnover and low-order pulsation, years for inner shell drift and infrared echoes of obscuration, decades for the build-up of layered arcs in the mid-infrared halo, and centuries for the assembly of the far halo. Against these core helium-burning spans, hundreds of thousands to a few million years, and the transition to later burning occurs when structure and mass allow not on a schedule readable from a single light curve. Within those bounds, the uncertainties listed above define the width of the present brackets on radius, luminosity, and mass loss, and thus on how close the star sits to a bluewood threshold. Among the brightest and most extended cool stars catalogued in the Milky Way, the luminous Hypergiant in Cephei stands beside a small company whose members share deep envelopes, molecule-rich spectra, slow winds and circumstellar dust that brightens in the infrared. The group spans classic red supergiants and rarer hypergiants scattered along nearby arms of the disk, each imprinting its own pattern of dimming polarization and emission. In Orion, a famous red supergiant dims dramatically a few years ago when a surface disturbance and a veil of dust crossed the line of sight. The light curve shows a broad descent and color changes that match additional extinction, while infrared data reveal a warm inner component that strengthens for a short time. The path of that event resembles the pattern described here, though the amplitudes, temperatures, and typical wind speeds differ, because the Orion star sits at lower luminosity and slightly higher gravity than the hypergiant in Cepheus. In Canis Major, an extremely extended red star is surrounded by a complex of arcs, knots, and outflows that span many thousands of astronomical units. Its outflow appears stronger on average and more chaotic, and its circumstellar chemistry shows bright silicate features that vary with time as condensations emerge and drift outward. The spatial reach of that envelope places it among the largest known cool stars by apparent extent at mid-infrared wavelengths, and it demonstrates how heavy mass loss sculpts a beaded rim and layered shells that echo what mid-infrared maps register around the hypergiant in Cepheus, though with differences in geometry and overall brightness that reflect distinct histories. In Cygnus, several very luminous red stars present deep molecular bands, slow winds of a few tens of kilometers per second, and halo asymmetries that correlate with polarization changes. Those stars illustrate the role of clumping and of preferred outflow sectors in creating angle-dependent extinction and in shaping resolved dust. In Scutum and Sagittarius, bright, cool supergiants within cluster environments provide anchors for distances and for ages. Their spectra show carbon, nitrogen, oxygen cycle fingerprints at the surface, like those discussed earlier linking winds and mixing across the class. Interferometry across the group consistently resolves asymmetric photospheres. In several cases, reconstructed images show bright sectors limb darkening that changes with wavelength and closure phase signatures that demand departures from simple round disks. Angular diameters shift with molecular band strength, reinforcing the idea that an effective radius depends on opacity and that extended molecular layers lift the apparent edge above the continuum in cool phases. The hypergiant in Cepheus fits comfortably inside this interferometric pattern, with its own measured elongation and box-like footprints in some epochs, and with multi-wavelength sizes that place the continuum radius below the molecular radius by a noticeable fraction. Spectroscopy likewise echoes across the set. Metalline forests and variable hydrogen profiles appear widely, with Persigny shapes marking outflows near the base of winds, and with forbidden lines in the faintest cases signalling thin hot patches. Molecular bands deepen as temperatures fall and relax as they rise, giving late G through early M classifications that wander subtly with phase. The Cepheus hypergiant's semi-regular rhythms of months to about a year mirror the broad peaks found in power spectra of other giants and supergiants, where overlapping convective and pulsational processes rather than strict periodic clocks dominate. Polarization behavior lines up as well. During seasons of enhanced inner dust, the degree rises and the angle drifts, pointing to scattering in a lopsided distribution, whose orientation shifts slowly. Similar patterns are reported for other cool luminous stars with fresh dust near the condensation front, and in each case the polarization helps to separate geometry from intrinsic changes in surface flux. When the camera steps from the star to the halo, mid-infrared maps across the class present rings and arcs broken into knots by instabilities in expanding shells. Alignment of beads along circular segments signals coherent ejections that have inflated and cooled as they drift, and the knots shine a little more brightly where density and temperature peak. The Cepheus hypergiant displays the same grammar of arcs and knots, with inner warm layers that shift on spans of years, and with outer cool layers that store the mass loss story over decades to centuries. Differences inside the family become instructive rather than contradictory. Some red supergiants show terminal speeds only a little lower or higher than those seen here, but their rates of shedding mass are smaller, and their halos remain less prominent at far infrared wavelengths. Some hypergiants at similar luminosity present more erratic light curves with larger excursions, perhaps reflecting stronger coupling between pulsation and dust condensation, or a different balance of clumping. In a few objects, detached shells at large radii suggest discrete past eruptions, while in others, including the Cepheus star, the record can be read as a sustained wind punctuated by enhancements that blur with distance. The position of each star in the Hertzsprung-Russell plane spans the same narrow band of very high luminosities and cool temperatures, where radii reach thousands of solar units, and surface gravity sinks to levels that let relatively gentle pushes lift gas. From this vantage, the Cepheus hypergiant sits on familiar ground, with size and power in ranges comparable to several of the largest cool stars catalogued, and with a spectrum that mixes deep metal lines, molecular bands, and wind signatures. Placing the star among counterparts also clarifies the roles of environment and projection. Some pairs lie in fields free of bright ionized complexes, simplifying extinction estimates, while others, like the Cepheus object, lie against glowing hydrogen and scattered light that complicate background subtraction. Some live within compact clusters where distances are tied to isochrones, while others drift in looser associations with only kinematic anchors. The comparison encourages the same caution here that is applied elsewhere, treating distances as brackets and temperatures as effective means across patchy surfaces. The wind physics carries over broadly. Dust-mediated acceleration sets the momentum budget near the base, where temperatures allow condensation line driving grows in importance as surfaces warm toward the blue, and clumping modulates how brightness maps to mass. Across the group, momentum ratios of wind to radiation point to multiple interactions of photons with grains and to scattering that keeps photons trapped long enough to share momentum widely before escape. The Cepheus hypergiant's rates and speeds fall within that envelope, reinforcing the view that it draws from the same engine, with local details governed by its envelope structure and recent history. When the observational record from the last few years is laid beside the archives for other giants, the deep dimming episodes show kinship in colour, paths, polarization, growth, and mid-infrared echoes. The shared sequence begins with strengthened asymmetric line profiles, and small reddening continues into reduced visible flux, with rising polarization and slightly warmed inner dust, and ends with recovery that leaves a new shell in the inner halo. Interferometric seasons collected before and after such intervals in multiple objects confirm that the brightness map across the disk rearranges, while the apparent diameter in molecular bands swells and contracts by several % in step with other diagnostics. In these ways, the hypergiant in Cepheus becomes one example in a small, diverse and revealing census of very luminous, cool stars that send gentle winds and intermittent dusty veils into their surroundings. Each member of the census shows how extended convection, weak surface gravity and radiative coupling shape a living envelope, and each supplies pieces that help interpret the others. The Cepheus star's placement against a structured field, its variable angular size and colour, its slow wind and layered halo, and its seasons of obscuration read coherently within that shared grammar, and its parameters occupy the overlapping ranges defined by the group.